Hi everyone. So in this video we are going to see assignment 5 and this assignment is fusion special. What do I mean by that? Fusion special, that means these questions are not that straightforward. If you are studying it for the first time, you cannot solve it by your own. You have to watch the solution, then only you should solve it. So those who have studied analog electronics before as well, they can try solving it on your own, but these are very good questions. In the GATE examination, these questions are not asked yet, but in the upcoming examination, these questions will certainly be asked. And in the interview also, these questions are asked. In the interview, they ask you the Vx versus Ix waveform, these kind of questions they ask. So in this video, we are going to solve around 9 to 10 questions. It will be a long video, it can be of around 2 hours, I guess. So around 9 to 10 questions we will see, and in each question you will learn something new. So have the patience, sit with notes, paper and pen, and then watch the solution. And once we are done with the question, try solving it on your own, then move to the next question. So these questions will build your concept to the next level. So we'll start one by one. So this is the first question. This question has 3 parts. You have to draw Vx versus Ix curve for this particular circuit. Your Vt value is given. This is your Ix value is given, and Vx value you are sweeping from 0 to 3 volts. Sweeping, that means I am increasing from 0 to 3 volt. And you need to plot Gm versus Vx curve as well. The definition of Gm is also given, that is del ID upon del Vgs. Same will be happening with this circuit B. Here also again Vx versus Ix, Vt value is given, Gm you also know, so Vx versus Ix and Gm versus Vx as well. Those you need to draw. This is the third circuit. Now this is a different kind of question. In this one, V in value is given. Again, we are sweeping V in value from 0 to 3 volt. You have to plot V0 versus V in now. Okay. In this question, Vx versus T, Ix versus T. Vx waveform with respect to time, Ix waveform with respect to time. Did I miss any question? No. Then this is the next one. Same question. This is the next one. And then this is the next one. Well and good. So we will solve it one by one. Don't be in a hurry. Have the patience and see the solutions. So you have to draw Vx versus Ix. This is the first circuit. I am drawing it on the next page. So this is our first circuit, circuit A. So tell me, what is the VDS value here? Since we need to write down the current equation, so I need to write down the value of VDS, VGS, VT, VO drive. Then I need to see in which region it is working, saturation or linear. If it is working in saturation region, the current equation will be different. If it is working in linear region, current equation will be different. So what is your VDS? VDS is 3 minus Vx. What is your VGS? That is also 3 minus Vx, because drain and gate are shorted. Drain and gate are shorted. What will be your VT? VT will be 0.7 volt. So what will be your VO drive? VO drive would be VGS minus VT. That would be 2.3 minus Vx. This is your VDS. This is your VO drive. What do you see here? Your VDS is always greater than VO drive. Always. Right? Always. Irrespective of the value of Vx, no matter how much you increase or decrease Vx, VDS will always be greater than VO drive. Do you agree with this point? Because what is VDS? It is 3 minus Vx. Let's just say Vx is 1. So what will be your VDS? 2. What will be your VO drive? VO drive is 2.3 minus Vx. If Vx is 1, VO drive would be 1.3. So always 2 will be greater than 1.3. Simple mathematics is there. It will always be true. Right? No issue with that. VDS is always greater than VO drive. That means it will always be in saturation region. So one thing you understood here is that I will write down a separate note. That is, if gate and drain are shorted and drain are shorted. Shorted means they are at same potential. If drain and gate are shorted, the MOS will always be in saturation. MOS will always be in saturation. Right? This is your NMOS. Drain and gate are shorted. Drain and gate are shorted. Drain and gate are shorted. So your VDS value will always be greater than VGS minus VT, because here VDS is equals to VGS. VDS is equals to VGS. Something is getting less from VGS. VDS is equals to VGS. Now if something is getting less here, that means this will be certainly greater. That's it. And similar thing will happen with NMOS as well. This is your NMOS. This is your NMOS. Now these are shorted. This is your gate and this is your drain. So here VSD, this is source, this is source. Here your VSD is always greater than VSG minus VT. VSD is greater than VSG minus VT, right? So it will always be in saturation. You have to remember this. If your VDS, if your gate and drain are shorted, the device will always work in saturation region. The region is simple. You can directly see it because VDS will always be greater than VO drive or VGS minus VT. Well and good. So this was the thing that we understood. So my device is working in saturation region. So what will be the equation of IX? That would be some constant. That would be mu n CXWYL. So some constant. I just need to draw the graph. I don't need the values. I need to draw the graph. So some constant into VGS minus VT whole square. VGS minus VT is this 2.3 minus Vx whole square. So this will be my Ix equation versus Vx. So if my Vx increases, my Ix decreases, right? If my Vx increases, I am drawing Vx versus Ix. Sorry, Ix versus Vx, I should say. Ix versus Vx. So if Vx is 0, this is my Ix. Some k into 2.3 square. No need of values, you just need to draw the graph. Now if Vx is increasing, the Ix will decrease like this, right? Now tell me one thing, what will be this potential? When will the Ix current be 0? When Vx is 2.3 volt, right? When Vx is 2.3 volt. When Vx is greater than 2.3 volt, what will happen? When Vx is greater than 2.3 volt, what will happen? Your VGS would be less than 0.7 volt, right? What is your VGS? VGS is 3 minus Vx. If it is less than Vt, what is Vt? Vt is 0.7. If it is less than Vt, that means if Vx is less than 2.3 volt or greater than 2.3 volt, sorry, if Vx is greater than 2.3 volt, what will happen? The device will go into cutoff, right? So I will write it in better manner. So for cutoff, what is the condition for cutoff? That your VGS should be less than Vt. What is your VGS? 3 minus Vx should be less than 0.7. That means your Vx is greater than 2.3 volt. So when Vx is greater than 2.3 volt, your ID will be equals to 0 ampere. Not ID, I can write Ix. Ix equals to 0 ampere. So till 2.3 volt, it will decrease, and after that it will be 0 ampere voltage. Now people will say, sir, if I put Vx equals to 2.4 volt in this equation, then what will happen? Sir, the current would be K into 0.1 square. No, the current will be 0. The current will be 0 because this equation is valid only for Vx value 0 to 2.3. That's it. If your Vx value is greater than 2.3 volt, your Ix will always be 0. So this thing you need to keep in mind, and this thing you need to keep in mind. That if I increase further Vx, my VGS value will be lesser than 0.7. If my VGS value is lesser than 0.7, that means if my VGS value is lesser than Vt, then my device will go into cutoff and the current will be 0. That's it. Right? Well and good. So this is the expression of Ix versus Vx we have drawn. Now talking about GM. Device is always device, or I can write MOS. MOS is always in saturation. So what is the GM value for saturation? If you remember previously, we have studied it. What is the GM value for saturation? Some constant, I can call it K dash, some constant into VGS minus VT, right? Say yes or no. It will be mu n Vx W by L Vgs minus Vt, right? This is the expression. So Gm, what will be Gm value? K dash into what is Vgs? Vgs is, what is Vgs minus Vt? That is 2.3 minus Vx. That's it. 2.3 minus Vx. That's it. This is your Gm. So Gm versus Vx curve you can also draw. MOS is always in saturation for Vx equals to 0 to 2.3. For Vx value 0 to 2.3, then only it is in saturation. When Vx is greater than 2.3, what will happen? Ix will go to 0. If Ix is 0, then certainly Gm will be 0. If there is no current, there is no meaning of Gm, right? So certainly Gm will be 0. So for Vx greater than 2.3, Gm is 0. Otherwise, it is following this equation. We are going to draw Gm versus Vx curve. If Vx is 0, then this is your Gm. K dash into 2.3. And if Vx is 2.3 volt, you can put equal here as well, because at 2.3 as well, it will become 0. So it is decreasing like this. After that, it is going towards 0 till 3 volt. Well and good. That's it. So this is the curve. So what was this question? Everything was given. You got to know that device is working in saturation region. When it is working in saturation region, you could write the equation of current. It is working in saturation region for Vx value 0 to 2.3 volt. Then you could write the equation of current. You could draw the Ix versus Vx waveform. After that, you got to know that if Vx is greater than 2.3 volt, what is happening? The device is going into cutoff region. If it is going into cutoff region, then the current would be 0. That's it. And also, what did you understand? If your drain and gate are shorted, the device will always work in saturation region. Now, talking about GM formula we already know. Some constant into VGS minus VT. Why we are not considering about constant? Because we just need to draw the curve. That's it. Nothing else. So, constant into VGS minus VT. VGS value we know 2.3. VGS value is Vgs minus Vt value is equals to V overdrive only, that is 2.3 minus Vx. Then we could draw the curve, and if Vx is greater than 2.3 volt, the current would become 0, and if current becomes 0, then your Gm would always be 0. So curve goes like this and then this. That's it. Say yes or no. Understood? Everything is clear? Let's move towards second question. This question is better than the previous one. So I will write down the values which are given. What was the values given? Vx you are sweeping from 0 to 3 volt. Vt value was 0.7 volt. That's it. Okay. Now, what people will think if they are watching this question for the first time, what they will say, sir, here VGS is equals to 1 minus 1.9 volt, that is equals to minus 0.9 volt, that is less than VT. This shows that your Ix will always be 0 ampere. Now, this line is completely wrong. Why so? This is completely wrong. Why so? I told you one thing. Source and drain are not absolute. This is what we are going to do. First, we will see what kind of device is that. This is NMOS. If this is NMOS, that means drain will be at higher potential and source will be at lower potential. The one which is at higher potential, that will be drain. The one which is at lower potential, that will be source. And in case of PMOS, one which is at higher potential, that would be source, and one which is at lower potential, that would be drain. A current will always flow from high potential to low potential. That's it. This is what I told you to remember in the complete MOS physics. Some equations and this thing. This is a very important thing. A lot of teachers don't teach this thing, and in the examination, if they ask these kind of question, you will be messing it up. You are sweeping your Vx value from 0 to 3 volt. For 0 to, if your Vx value is from 0 to 1.9 volt, what will happen? If your Vx value is from 0 to 1.9 volt, this potential will be low, right? And this potential will be high. If your Vx value is between 0 to 1.9 volt, this will be low, this will be high. What will happen? This will act as a drain. This is at higher potential and this will act as source. Say yes or no. Okay, so let's write it down. I should not write it in the question itself. So what will happen is that this is your given circuit. So here Vx is at lower potential, since this is at lower potential, and this is at higher potential. So this will become drain and this will become source. The current will be from drain to source, right? Current will be from drain to source. So you can show it something like this. This is your drain, which is at 1.9 volt. So it will be from drain to source in this direction. The current will be from drain to source. Basically, this has become your source. So it is looking like this only now. Just the opposite I have drawn. I have drawn it in this manner. This point is going here, this point is going here. That's it. Now this has become source. And this is your 1 volt. And your current will flow in this direction. Now, can I write down the value of VDS, VGS and VT, all those things I can write. So what is the value of VDS now? VDS, drain to source, 1.9 minus Vx. What is the value of VGS? VGS, gate to source, that is 1 minus Vx. What is the value of VT? That was given is 0.7 volt. This is not PMOS, okay? In the initial phase, you can get confused. Sir, this is PMOS. No, no, no. In PMOS, this is the scene. In PMOS, what is the scene? This is the scene. And this is source there. Now I am drawing like arrow like this. Arrow is going outward. If the arrow is going outward, that means it is certainly NMOS. But the source has changed. Source is the upper one and drain is the lower one. This is not your IX, this is actually ID. This is actually ID. IX direction is always from Vx to 1.9. They have given the IX direction in the question itself. In the question itself, they have given the IX direction. That is from Vx to 1.9. Vx to 1.9. So this is IX. But first I will write down the value of ID. Then I will see what I need to do. And what will be your V overdrive? V overdrive would be 0.3 minus Vx. Till this point, everything is clear or not? First thing we saw there is that Vx value is increasing from 0 to 3 volt. Then we got to know that till 1.9 volt, it will be interchanged because the upper potential is low. That means that will act as source and 1.9 will act as drain. So current will flow from drain to source, higher potential to lower potential. So current will flow like this and that has become source. So VDS value is 1.9 minus Vx. VGS value is 1.9 1 minus Vx. VT already given and V overdrive is also there. What did you see here? That your VDS is greater than VGS minus VT. If you are getting confused with this diagram, you don't need to draw it. You just get to understand that okay, this is source, this is drain. Then VDS I can write, VGS I can write, everything I can write. So here you can see is that your VDS is greater than VGS minus VT, which is V overdrive. VGS minus VT. That means it is also working in saturation region. But till what point it will work in saturation region? This is in saturation region. You always need to see cutoff region, when it will go into cutoff. For cutoff, your VGS should be less than VT. Your VGS should be less than VT, or I can say your V overdrive should be less than 0. Say yes or no. What is V overdrive? VGS minus VT only. V overdrive is VGS minus VT. So V overdrive should be less than 0. That means your Vx should be greater than 0.3. So for cutoff region, your Vx should be greater than 0.3 volt. Say yes or no. If Vx is greater than 0.3 volt, your device will go into cutoff. And this is all happening for 0 to 1.9 volt. So what did we get to know here is that for 0 to 0.3, your device is in saturation region. Your device is in saturation region. Here VDS is greater than VGS minus VT. So it is in saturation region. So what will be the expression of ID? Expression of ID I am writing. Expression of ID. Expression of ID would be K into VGS minus VT. That would be K into VGS minus VT 0.3 minus Vx whole square. This is your ID. But here you could see that the ID direction is from 1.9 to Vx. ID direction is 1.9 to Vx. But Ix direction is from Vx to 1.9. So Ix is negative of ID. So what will be your Ix? That would be minus K into 0.3 minus Vx whole square. This is your Ix. Now you need to plot, this is your Ix, and then one more thing you know is that for 0.3 to 1.9 volt, it is going into cutoff. If it is going into cutoff, that means your Ix is 0. Ix is 0 ampere. I can write down the value of Gm as well, right? I can write down the value of Gm as well. So here what will be the value of Gm? If current is 0, then Gm is certainly 0. Here what is Gm? Gm is always some constant K dash into Vgs minus Vt. Some constant into what is Vgs? Vgs is Vgs minus Vt. What is Vgs minus Vt? That is 0.3 minus Vx. That's it. This is your Gm. Any issue with that? Right? Yeah. So this was the expression of Gm. So Gm expression we have, I expression we have, for 0 to 1.9 volt we have. So now we can draw the characteristics. So Ix versus Vx I am going to draw, and in the next I am going to draw Gm versus Vx. Ix, sorry, Ix versus Vx, and then this is Gm versus Vx. So if Vx is equals to 0, then your Ix is some negative value. If Vx equals to 0.3, it will go to 0. So it goes something like this, right? After 0.3, it is 0 only. The response is not linear, right? It follows the square equation. So quadratic like this, not linear. And till 1.9 we have concluded. After 1.9, what will happen? We will see it, because after 1.9 the drain and source will be interchanged. Here drain and source are like this. This is drain, this is source. After 1.9, that will be drain, that will be source. So we will analyze that, but till 1.9 we are drawing. This is 1.9 volt. So till 1.9 volt, this is what we have got. For Gm, what is the scene for Gm? At 0, it is some voltage, some value, that is k into k dash into 0.3, and at 0.3 it will be 0. At 0.3 volt it will be 0. And after that, till 1.9 it remains 0 only. So this we have done till 1.9 volt. After 1.9, what happens? That we will check now. For Vx greater than 1.9 volt, what will happen now? This was your Vx given, this was your 1.9 volt given, and this was 1 volt. This will become higher potential. That means this will be drain, this will become lower potential, this will be source. What do you see here? And this is certainly gate only. There is no doubt in that. Gate is always fixed. This is gate, that is fixed. So what do you see here? What is your VGS here? 1 minus 1.9. That is minus 0.9. That is less than VT. MOS is off. And if MOS is off, then your Ix is 0 ampere. And your Gm is also 0. That's it. So after 1.9, nothing changes. After 1.9, what did we get to know is that your Ix is 0, so certainly your Gm is also 0, because VGS value is minus 0.9, which is less than VT. So we can copy the same diagram for the final one. So what I am going to do, I am just going to increase the Ix value, that's it, till 3 volt, which will be 0 only. And after in this one, for Gm as well, I am going to increase it till 3 volt. It will always be 0. That's it. So when we saw this question for the first time, what did we understood? Vx and 1.9 will be interchanged. The upper one will be source, lower one will be drain, because that is at lower, drain is at higher potential, source is at lower potential. So 1.9 is the high, and till 1.9 volt Vx will be low. So the current direction will be in this direction now. So we could write down the value of VDS, VGS, VT, then I could write down the expression of current ID, and ID is equals to minus Ix. Then I could write down the expression of Ix as well. Then the GM formula I know, that is K, some constant into VGS minus VT. VGS minus VT I know, the constant value I don't need to bother about. So that would be 0.3 minus Vx. But I got to know that after Vx is greater than 0.3 volt, the device will be in cutoff. The current will be 0. If the current is 0, then GM will certainly be equals to 0. This we analyze till 1.9 volt. After 1.9 volt, what happens is that my VGS is less than VT. My VGS is minus 0.9. That is less than VT. So my Ix and GM both will be 0. That's it. So this is the second question. Well and good. Let's move towards the third question. You have to solve it on your own. Now you can try doing it on your own. The same thing is happening. I will write it down. What is happening? Vx is sweeping from 0 to 3 volt. Vt value is given, that is 0.7 volt. Here it will be Vtp, because since this is NMOS, sorry, PMOS. This is PMOS. You could directly see the arrow is inward. If the arrow is inward, that would be PMOS. This is 0.7 volt. Well and good. Everything is crystal clear. Okay. Now you have to draw Vx versus Ix. In case of PMOS, which is at higher potential? Source is at higher potential, right? In case of PMOS, source is at higher potential. So what do you see? For Vx equals to 0 to 1.9 volt. What is happening? This is 1 volt. This is Vx, and this is 1.9 volt. This will be at higher potential. This will be at lower potential. If it is at lower potential, in case of PMOS, it will be drain. And this will be, since it is at higher potential, this will be source. Well and good. Everything is clear. What will be the direction of current from high potential to low potential? The direction of current will be this. Given Ix is this. Given Ix is this. But actual ID will be this. I don't need to draw the circuit. I can directly write down the VDS, VGS, all those values. What will be my VSG value? Why I am interested in VSG? Because I am talking about PMOS now. So what is my VSG? VSG, that would be 0.9 volt. Source to gate. What would be my VSD? VSD, that would be 1.9 minus Vx. What would be my V overdrive? That would be VSD minus VT. Sorry, VSG minus VT. Sorry. VSG minus VT. So 0.9 minus 0.7, that would be 0.2 volt. Everything is clear? Say yes or no. So what do you see here is that what is your VSD? So let's write down the condition. This is your VSD. VSD is depending on Vx. So your region of operation will also depend. Are you getting this point or not? Your VSD is depending on Vx. So your region of operation will also depend on Vx. How? For saturation, what do you need? Your VSD should be greater than V overdrive, right? What is your VSD? 1.9 minus Vx. That should be greater than V overdrive, that is 0.2 volt. So Vx should be less than 1.7 volt, right? Vx should be less than 1.7 volt. This you got to know. Other thing you got to know is that your V overdrive is always greater than 0. So MOS is always on. MOS is on. V overdrive is always greater than 0. So your MOS is always on. Here, what was the scene? Your V overdrive was depending on Vx. So if Vx was greater than 0.3, your MOS was getting off. Here your V overdrive is not depending on Vx. 40 to 1.9 volt. This we are considering only 40 to 1.9 volt. Forget about 3 volt anything. 40 to 1.9 volt, your V overdrive is not depending on Vx. Your V overdrive is constant, that is 0.2 volt. That means MOS is always on. Now I got to know the condition for saturation. The condition for saturation is your Vx should be greater than 1.7. Then what do you understand by that? If your Vx is less than 1.7, then your device will be sorry, if your Vx is less than 1.7, then your device should be in saturation region. This is given, this I derived. But if your Vx is greater than 1.7, what will happen? Your device will be in linear region till 1.9 volt. This we are talking about till 1.9 volt. Till 1.9 volt we have talked about. Say yes or no, everything is crystal clear. So for Vx less than 1.7 volt, what will happen? Vx less than 1.7 volt. What will be your ID? ID would be some constant into Vsg minus Vt whole square. So some constant into what is Vsg? Vsg minus Vt. So this will be Vsg minus Vt, 0.2 whole square. So ID is a constant current. And what is your Ix? Ix is negative of ID, right? Because ID is flowing from 1.9 to Vx. ID is flowing from 1.9 to Vx, but Ix is flowing from Vx to 1.9. Ix is flowing from Vx to 1.9. So ID is negative of Ix. So Ix would be minus K dash 0.2 whole square. So this will be your Ix voltage. This will be your Ix. So this we are talking for 1.7 till 1.7. Now what about GM? What will be your GM? So GM would be some constant. It could be anything. Some constant K I am writing. It could be any constant into Vsg minus Vt. What is the value of Vsg minus Vt? This is 0.2, right? This will be your GM. Say yes or no. Well and good. Yeah. So this I have written Ix and GM value for Vx less than 1.7 volt. Now for 1.9 to 1.7 volt. 1.9 to 1.7 volt. 1.9 to 1.9 to 1.7 volt I am going to write. So what will be your Ix? What will be your ID? Tell me. What will be your ID? Some constant. It can be any constant. I have to give different name. Some double I am writing. Some constant into Vsg minus Vt. Vsg minus Vt into Vsd minus Vsd square by 2. Some constant Vsg minus Vt. What is Vsg minus Vt? That is V out, right? Into that would be 0.2 into Vsd. What will be your Vsd? That would be 1.9 into Vx. 1.9 minus Vx, sorry. This would be the equation, right? Now this is your ID. What will be your Ix? Sorry, this is your ID. And what will be your Ix? Ix will certainly be negative of this. That's it. Just the negative of this. This will be your Ix. Negative of ID. That's it. Now how will you draw it? Correct expression is very much difficult, but we can do an approximate expression, right? Drawing the correct expression of this very much difficult, because here you have linear term as well as square term as well. You need to simplify it in a very great manner, then you need to differentiate it, then you can draw. But but intuitively we can also draw. That I will tell you when we draw the characteristics. First we are writing down the expressions. And what will be your GM? Do you remember the GM formula for triode region? GM formula for triode or linear region. Do you remember the formula? What was the formula? Some constant, then Vgs minus Vt get cancelled. Some constant into Vds, that's it. Some constant into Vds, right? This was the formula. Because the expression was mu n Cx W by L, Vgs minus Vt into Vds. Just you need to differentiate it with respect to Vgs. So what you will get? This will be 1, only Vds, and this will be 0. So some constant into Vds. So some constant into Vds. Sorry, not Vds. If we are talking about PMOS, it would be VSD. So what is the value of VSD here? 1.9 minus Vx. So drawing this is not that much of task. This will be very easy. So this is your GM. So you have all the expression. Now you need to draw the curve. The curve we are going to draw only till 1.7. Sorry, 1.9. 0 to 1.9. So 0 to 1.9 we are going to draw. After 1.9 what will happen, that we will see. But till 1.9 we can draw. Vx versus Ix versus Vx and GM versus Vx. This is Ix versus Vx, and this is Gm versus Vx. So Ix versus Vx till 1.7 volt. This is 1.7 volt. So till 1.7 volt, what is the expression of Ix? That is some constant value. This is constant, right? This is also a constant value. This k will be some negative, k will be some positive value only, mu n c x w by l, whatever the k is. So that will be some positive value only. In this case, it would be mu n c x w by 2l, and in this case, k would be mu n c x w by l. So that will be some positive value only. So complete value will be negative. So Ix is negative. Ix is negative. Some negative constant voltage. And till 1.7, this will be some positive voltage. This will be some positive voltage. Well and good. Now, after that, what happens? Look, after that, if Vx increases, then this value will decrease. This value will decrease, and this value will also decrease. Which value will decrease more? This is my question. If Vx increases, this value will decrease, and this value will also decrease. Which value will decrease more? Vx will increase from 1.7 to 1.9. Let's check that out. If your Vx is 1.8, what will be this value? 0.1. If your Vx is 1.8, what will be this value? 0.01 square by 2. Very less, right? Very less. If your Vx is 1.7, what will be this value? 0. It will be 0.1 square by 2. I am really sorry. It would be 0.1 square by 2 if Vx is 1.8. So overall value will be 0.01 by 2. Very less. If your Vx is 1.7 volt, what will be this value? If Vx is 1.7 volt, this value will be 0.2 whole square by 2. So it would be 0.04 by 2. 0.02. This is also very less. You can ignore this factor. Here, this particular value is very less. For the range 1.7 to 1.9, you can simply ignore this factor. That's it. If you simply ignore this factor, what happens? If your Vx increases, the current magnitude decreases. The magnitude of current decreases, but since there is negative direction, negative sign, so it will go like this. At Vx equals to 1.9, what will be the current? At Vx equals to 1.9, this is 1.9, 1.9, the current will be 0. At Vx equals to 1.9, the current will be 0. So I know the current will go like this. The current will go like this from here to here, right? It will go nearly linear. Although this expression is also there, so it will not be completely linear, but nearly linear it would be. Nearly linear. Nearly linear. The word is complex. Okay, are you getting this point? If your Vx is from 1.7 to 1.9 volt, what is happening is that if your Vx is increasing, your current magnitude is decreasing. Current magnitude is decreasing, but the current is in negative direction. So in positive direction, it would increase. And at 1.9 volt, the current would be 0. I know that at 1.9 volt, the current would be 0. So it will increase like this. And magnitude is decreasing. What is the magnitude here? Let's just say magnitude is 3 ampere. Let's just say magnitude is 3 ampere. After that, the magnitude will be 2 ampere. But actually, value is increasing. Minus 3 is less than minus 2. But the magnitude is decreasing. Are you getting this point? So magnitude is decreasing. And nearly linear it will go. But not completely linear. Why so? Why not completely linear? Because this factor is also there. But this factor is very low. So you don't need to consider it. So it will go like this. And what about this? This will certainly be completely linear. At 1.9 it will be 0. So this will certainly be linear. This will be your 1.9 volt. This is a linear expression. So it will linearly go down. Linearly go down. That's it. So till 1.9 we have wrote it down. For Vx greater than 1.9 volt, what will happen? Now this is the task. For Vx greater than 1.9 volt, what will happen? Let's check that out. So for Vx greater than 1.9 volt, what will happen? This will be at higher potential, this will be at lower potential. So I can draw the circuit. higher potential, lower potential. If it is at higher potential, this will become source and this will become drain, right? So what will be your VSD value? That would be Vx minus 1.9 volt. What would be your VSG value? That would be Vx minus 1. What would be your Vt value? That would be 0.7 volt. So what will be your V overdrive value? V overdrive would be VSG minus Vt. Everything is correct. VSG is Vx minus 1. Vt is 0.7. So V overdrive would be VSG minus Vt. And VSD is Vx minus 1.7. So here your VSD is greater than V overdrive. Say yes or no. No. VSD is not greater. VSD is lesser than V overdrive. VSD is lesser than V overdrive. Why so? Because this potential is same. Vx minus 1.9 versus Vx minus 1.7. Let's just say if Vx is 2, so this value will be 0.1 volt. If Vx is 2, this value will be 0.1 volt and this value will be 0.3 volt. So this is greater. This value is greater. This value is greater. And that value is V overdrive. So V overdrive is greater. If V overdrive is greater, that means it is working in linear region. It is working in linear region. Right? So it is working in linear region. And what is the direction of this current? That is Ix, and Id will also be in the same direction. I can write down the expression of Id and Ix. This lecture will take time, but certainly you are going to learn a lot of new things here. And this will help you a lot in the interview as well as in the written test of any company. Also in the GATE examination, I am expecting these kind of questions to come very quickly. And these are very conceptual questions. And if you have the 4 options, it will be easier for you. But if you don't have any option, then it is a bit difficult. So what is ID? ID will be some constant. And we are writing for Vx greater than 1.9 volt. Vx greater than 1.9 volt. It will be some constant into VSG minus Vt into VSD minus VSD square by 2. Some constant. VSG minus Vt. What is VSG minus Vt? That is V overdrive. Vx minus 1.7 into what is VSD? VSD is Vx minus 1.9 minus 1.9 minus Vx minus 1.9 square by 2. This is your ID or Ix expression. Now the expression looks very complex. Here you cannot even ignore any factor. Why so? Because if Vx equals to 3 volt, then this will become significant. If Vx is equals to 3 volt, this will become significant because 1.1 square by 2. This is a significant value, 1.21 by 2. It is a significant value. So you cannot ignore it. But one thing I know is that if I increase my Vx, if I increase my Vx, what will happen? VSD will increase and VSG will also increase. If I increase my Vx, this factor will increase, this factor will increase, this factor will also increase. The doubt is this factor will increase, this factor will increase, now this factor will also increase. So overall this factor will increase and this factor will also increase. So the value of ID will increase or decrease. This is the doubt. The expression you have wrote, if Vx increases, this factor will increase, this factor will increase and this factor will also increase. Tell me one thing, overall value will increase or decrease? It will increase only. Why so? Do you remember the ID versus VDS curve? ID versus VDS curve. If I increase my VDS anyhow, my current increases. But in linear region, if I increase my VDS, my current increases. But what is the formula? Some constant into VGS minus VT into VDS minus VDS square by 2. So there also you can argue, sir, this value is increasing, this value is also increasing. So why this overall value should increase? Because this value doesn't increase that much as VDS. Are you understanding this point? VDS increases more. and this value doesn't increase as much as VDS. So it will increase only. The argue could be, sir, VDS is also increasing, VDS square by 2 is also increasing. So increase minus increase, what will happen? Overall increase or decrease? It can be anything, but VDS square by 2 will not increase that much as VDS. So while current increases only. The same thing is happening with ID versus VSD as well in case of PMOS. So here the current is going to increase only, but not linearly, but square relation would be there. So current will increase. And what about GM? Do you remember the formula of GM for triode region? That is some constant into VSD. So what is your VSD? VSD is Vx minus 1.9, right? So it is certainly going to increase as well. Vx minus 1.9. At 1.9 it will be 0. Is there everything correct? Let me check. Yeah, so the GM formula is correct. Some people may have a doubt. In the initial question I wrote the GM is del ID upon del VGS. So what is ID here? Is ID equals to IX or ID is the current that we are taking? So in the question it needs to be defined what is ID. So ID I will write current from drain to source in case of NMOS and current from source to drain in case of PMOS. This should be defined in the question only, and also in the question GM value should be given, that should be del ID upon del VSG. Look, if they have given that your GM is del IX upon del VGS, then there would be no problem. But if they are calling ID, then they have to define, because our ID direction is getting changed in the question, right? Our ID direction is getting changed. Initially, here my ID direction was upward. Now what is my ID direction? For Vx greater than 1.9 volt. For Vx greater than 1.9 volt, what is happening? Oh, I forgot to tell, for Vx greater than 1.9 volt, this is becoming source and this is becoming drain. Did I tell you that? Yeah, here I told you. So yeah, this is my ID. Now this is my ID. That is getting changed. So here I don't need to write. So ID direction is getting changed. So based on that, my GM direction will also change. So GM is going like this. Now GM will increase. So they have to define in the question. Did you understand this point? The high chances is that they will define GM as del IX upon del VGS. They will define GM as del IX upon del VGS or del IX upon del VSG. If they are defining del ID upon del VGS or del ID upon del VSG, then they need to define what is ID. So ID is the current from drain to source in case of NMOS and current from source to drain in case of PMOS. So here the current from source to drain, this is the current. And in the previous case, the current from source to drain, this is the current. So this is the ID. And based on that, we are writing our GM equation. So K into VGS minus VT. Here also we wrote in the same manner K into VSD. Here also some constant into VSD. Crystal clear? Everything is clear, right? So based on the given equation, you need to find out the value of GM. For IX, there is no issue because IX direction is shown, but GM is the expression. So for that, they need to define it. Yeah. So IX versus VX curve we are drawing. So in the next page only I should draw, I guess. So this was the IX versus VX curve. So after that, after 1.9, it will increase like this. Because I told you, if Vx is increasing, the current will increase only, right? This expression will not increase that much, but this expression will increase. So the current will increase only. It will increase till 1 point. It will keep on increasing, but we are going to draw till 3 volt only. And if we are drawing GM versus Vx, if we are drawing GM versus Vx. I can just copy this one. GM versus Vx. So after 1.9, what is the scene? After 1.9, it is increasing in positive direction only. So like this, it is increasing. It will keep on increasing in the same manner, but we have to write down till 3 volt only. So this expression might seem a bit complex to you, going like this and then increasing, because the ID direction is getting changed. First GM was decreasing, then again increasing, because ID direction first was in this direction and then ID was this direction. So that's why GM expression is going like this. Are you understanding this point or not? Well and good. So in the question, ID direction should be defined. Understood? So these three questions we have seen. In the last problem, what was the scene? Three condition we saw. For Vx less than 1.9 volt, it is certainly interchanging. The upper one is working as drain, lower one is working as source. So current direction will be from source to drain. That is your ID. So then we go to know the condition of saturation and linear. So Vx less than 1.7, it is working in saturation. Vx greater than 1.7 till 1.9, it is working in linear. Then we could write down the expression. Ix expression we could write down, GM expression we could write down. And similarly for linear region as well. Then we could draw the graph. For Vx greater than 1.9 volt, it is working in the Vx will be source and 1.9 will be drain. And it is working in linear region. So for linear region, we could write down the expression of Ix as well. And then we could write down the expression of GM as well. And then we could draw the graph. Well and good. Now we are moving towards the different kind of questions. Here we just need to draw V0 versus Vin, and Vin value is getting swept. Vin value is getting swept from 0 to 3 volt. So let's check that. Let's check out what happens. Okay. Yeah. So this will be a very interesting question, and I have changed some values. Here RL value is very low, and you have to find the maximum value of V0 as well. You have to draw the graph, and also you need to tell me what will be the maximum value of V0. So let's start solving this problem. If I ask you one question, what is that question? I am asking you, what is the minimum value of Vin at which the transistor turns on? Approximate value. What should be the approximate value of Vin at which the transistor turns on? You are sweeping Vin voltage from 0 to 3 volt. What is your answer? 1.7 volt. Is that your answer? That means you want to say that for Vin less than 1.7 volt, MOS is off. Is that your statement? If this is your statement, this is absolutely wrong. Why so? Let's just say I am saying that at 0.1 volt my transistor is not turning on. If it is not turning on, then what is the potential at V0? 0 volt, because there will be 0 ampere current. The whatever the current that is flowing through MOS, the same current is flowing through RL. So there will be 0 current through RL. So V0 will be 0 volt. This potential is 0 volt and this potential is 1 volt. Which one is higher? This one is higher. Right? This one is higher. So if this is higher potential, that means this will be drain and this will be source. The current will flow in this direction. Are you getting this point or not? Initially, there is no current. When Vin equals to 0 volt, there is no current in the transistor. So V0 becomes 0. What I mean to say is that I will write down all these points now. Initially, MOS current is 0 equals to 0 amp. If that is 0 amp, that shows that V0 is equals to 0 volt. What will happen? V0 will become source, because that is at lower potential, and 1 volt would become drain. Right? Tell me one thing. Can this ever be source? Can this ever be source? Let's just assume that this potential, let's call this as x potential. So I am calling this Vx is becoming drain. Vx is becoming drain. Someday by some value, somehow your Vx, this potential is becoming source. Currently, this one is source and this one is drain. Currently, this is the scene. Let's just say sometimes it becomes source. Then what will happen? If this becomes source, then what will happen? The current will flow in this manner. Say yes or no. If this becomes source, if X potential becomes source, the current will flow in this manner. If the current flows in this manner, then what will be the voltage drop? Like this. Now this V0 voltage drop will certainly be lesser than 0. Say yes or no. If someday your potential X becomes source, if someday your potential X becomes source, then what will happen? The current will flow in this direction. The voltage drop at V0 will be negative. So here you are having negative and here you are having 1 volt. Which one is higher? This one is higher. Can this be source? No, drain. So the potential X can never be source. What did I do? I assumed that potential X is source. If I assume it to be source, then the current direction would be from up to down. If that is the current direction, then V0 will be negative. And if V0 is negative, that means drain potential is negative and source potential is at 1 volt, which is not possible. So what did I get to know? That 1 volt will always be drain and V0 will always be source. Say yes or no. No matter how I draw the circuit, V0 will always be source and 1 volt will always be drain. So this is what we are going to write now. So let's assume potential X is source. So we'll draw the circuit once again. This is the potential X which is at 1 volt. If it is source, what will be the ID direction? This would be ID direction. Then V0 will be negative. But Vs that is equals to Vx that is at 1 volt and V0 which is equals to Vd that is negative, and this is not possible. Right? The drain potential cannot be negative and source potential being positive and drain potential being negative. This is not possible. That means what does that show? That shows that X will always be drain. X will always be drain and V0 will always be source. That means this will always be at higher potential, this will always be at lesser potential than V0. So how will your diagram look like now? I can make the diagram like this. This will always be drain, this is source, this is source. Basically the current direction will be in this direction. The current direction has to be like this. So what I am doing, the current is flowing from 1 volt to outward towards V0. So this is how I can show it. This is RL and this is your V in. That's it. This is how your circuit should look like. This is your final circuit. Final circuit. Are you understanding this point or not? Did you get this point? I assume that if X is source and V0 is drain, then V0 is becoming negative and X is at 1 potential, which is not possible. That's why V0 will always be source and X will always be drain. So this is how I made it, and this is NMOS. Since this is NMOS, the direction of current will always be from drain to source. One thing also I got to know that V0 can never be greater than 1. So what is the maximum value of V0? 1 volt, right? That's it. The maximum value of V0 is 1 volt. But before that, let's solve the circuit now. So this is the circuit. This is our final circuit, which I have drawn here. Now, for V in less than Vt or V in less than 0.7 volt, MOS will be off. Say yes or no. Initially MOS is off, so V naught is at 0 volt. Initially MOS is off, so V naught is at 0 volt. So for turning on the transistor, you need VGS greater than VT. Initially V naught is at 0 volt. Initially V naught is at 0 volt. Until V in is less than 0.7 volt, MOS will be off. Are you agreeing to this point? Because you need VGS greater than VT, but here your VGS is less than VT. When V in is equals to 0.7 volt. At 0.7 volt, what will happen? Let's assume I consider transistor to be on. I am assuming the transistor is on. So at 0.7 volt, there will be some current here. If there is some current, there will be some voltage drop. It can be some 0.001 voltage drop. Why so? Because just as you turn on the transistor, what will happen? What is ID versus VGS curve? ID versus VGS curve. It goes like this. Just as your VGS is, just as the current flows, that value is very less, right? This value is very less. The current value is, this current value is very less. So very less amount of current flows here, very less. And this value RL is also very less. That means this V naught will also be very less. But it will be somewhat greater than 0, that's for sure. Your V in is at 0.7 volt. Your V in is at 0.7 volt and your V naught is 0.001 volt. That means your VGS is some 0.69999 volt something. Here also it will not turn on, but you can say that approximately nearly around 0.7 volt it will turn on. So I am writing when V in is equals to 0.7 plus volt. So just somewhat greater than 0.7, your transistor will turn on, because when you turn on the transistor, the ID is very small. That means V naught will be very small. So this I can write down. ID I can show. V naught I will remove. This also. MOS is on. When MOS just turns on, at that time ID is very small. And what is your V naught? That is ID into RL. That is also very small, right? Let's check the region of operation. What is VDS here? VDS is 1 minus V naught. What is your VGS? V in minus V naught. What will be your V overdrive? That would be V in minus 0.7 minus V naught, right? For saturation, VDS should be greater than V overdrive. So V in should be less than 1.7 volt. For saturation, your V in should be less than 1.7 volt. Are you agreeing to this point? Did I write it correctly? VDS should be greater than VGS minus VT, so V naught getting cancelled. V in should be less than 1.7 volt. When V in is less than 1.7 volt, it is in saturation region, and when V in is greater than 1.7 volt, it will be in linear region. Now since it is in saturation region, so the current should be constant. Is that so? Because we have studied in saturation region the current is constant. In saturation region the current is constant, but the current is constant only when this is for a particular VGS value. VGS value should be fixed. If your VGS value is fixed, then only the current will be constant. Here VGS value is fixed. No, value is varying on V in minus V naught. So the current is not constant. So let's take the condition for 0 to 1.7 volt. Let's see what happens. For our target is to find V naught. And what is V naught? V naught is ID into RL. So for finding ID, we need to know the region of operation. If we know the region of operation, we can write down the value of ID. So for V in equals to 0 to 1.7 volt, what will be your ID? ID will be some constant, right? Okay, some constant. into VGS minus VT square by 2. What is VGS minus VT? VGS minus VT is V in minus 0.7 minus V naught. V in minus 0.7 minus V naught square by 2 will be taken care in the constant only. So this is some constant into V in minus 0.7 minus V naught into whole square. So what will be your V naught? V naught is ID into RL. So basically your V naught would be K into V in, although these are not small signal, I have developed the habit of writing V naught like this. Actually V naught should be written like this. What is small signal? We will learn it, no need to worry. All this should be written like in this manner, V naught, the way I have written, but I have developed the habit of writing V naught like this. You just need to consider this is capital V naught. We are doing the DC analysis. If we do the DC analysis, we write in capital. If we do the AC analysis, we write in small. You will know the region in the next lecture, but just consider here we are doing DC analysis, so everything is large V naught. Capital letters, all are capital letters. And I have developed this habit, which is wrong actually. I should not develop this habit. So K into V in minus 0.7 minus V naught whole square. So what will be your V naught? V naught would be ID into RL. So K into V in minus 0.7 minus whole square into RL. So this will be your V naught value. If you see intuitively, what do you see? If your V in increase, then your gate voltage is increasing. That means your current should increase. If your current is increasing, then your V naught should increase. If your V naught is increasing, that means your source potential is getting decreased. If source potential is getting decreased, sorry, if your V naught is increasing, that means your source potential is getting increased. If your source potential is getting increased, that means the difference here, VGS, is getting decreased. Then the current should decrease. Did you understand this point or not? What I mean to say is that if Vin is increasing, then if gate voltage is increasing, current should increase. Because what is the current? K into VGS minus VT. VGS minus VT whole square. The gate voltage is increasing, then the current should increase. If the current is increasing, then V naught should increase. If V naught is increasing, then what is happening to VGS? Source potential is increasing, then VGS is going down. If VGS is going down, the current should go down. What do you think what will happen? The current will rise or fall? If I increase V in, the current will rise or fall? The current will rise only, but not very fast. The current will not rise like this. The current will rise slowly. Why is it so? Because if I increase V in, the V naught does not increase as much as V in. Did you understand this line? If I increase V in, the V naught doesn't increase as much as V in. Why so? Because RL value is very low. If you just increase V in, ID value is already very low. Because I told you, if your transistor is turning on, then ID value is low. RL value is very low. So V naught value will also be very low. V naught will increase, but very slowly it will increase. This is the assumption we have to make, or this is also a fact that always source potential does not increase as much as gate potential. When we study amplifier, you will also get to know that the gain will be less than 1. The gain will be less than 1. So V naught will follow input V in. If V in is increasing, V naught will also increase, but it will not increase as much as V in. Are you getting this point or not? It will not increase as much as V in. This is what I wanted to write. If I increase V naught, if I increase, not I, people will think this is current. If we increase V in, I will increase, V naught will increase. But V naught will not increase as much as V in. V naught will increase, but not as much as V in. Are you getting this point? So for saturation region till 1.7 volt, I am drawing V naught versus V in. So V naught will just keep on increasing. But till what point it will increase, we don't know. After 1.7 it will be in saturation region, so we will talk about that. So it will increase like this. So at 1.7 volt, the value V in value is 1.7 volt. V naught value will be very less. It will be very less than 1.7 volt. Are you getting this point? Because V naught is increasing, but not as much as V in. V in has increased from 0 to 1.7. V in has increased from 0 to 1.7. The increase is 1.7 volt. But in case of V naught, it will not increase that much. Practically, it will increase nearly around 0.2 volt or 0.3 volt only. Very less it increases. So not that much. Okay. So it increases very less. I will draw a better diagram. Well and good. After 1.7 volt, what happens? For V in greater than 1.7 volt, it will be large. For V in greater than 1.7 volt, what happens? A diode is in saturation. No, sorry, triode. Diode is in triode region. So what is your ID value? ID value, some constant into VGS minus VT. What is your VGS minus VT? VGS minus VT is this V in minus 0.7 into VDS. What is VDS? VDS is 1 minus V naught. This is your ID, and your V naught would be ID into RL. Right? Now again you will have a doubt. Sir, what will happen if we increase V in? The V naught will increase or it will decrease? It will again increase. If you are increasing the gate potential, it is certain that your current is going to increase and V naught will increase, but not as fast as it could. Are you getting this point? It cannot increase as fast as it could. It will increase slowly only. So the waveform will be same. In the examination or in the interview, if they ask you to draw the waveform, you will draw it in the same manner only. You will just tell them, sir, it will keep on increasing. Now the question from their side would be coming is that, okay, I admit it will keep on increasing, but till what value it will increase? That would be their question. Oh, I can make it also better. Okay, that seems good. Now their question would be, what would be the maximum value of V naught? Tell me. That would be 1 volt only. Why so? Why is it so? Because what was your circuit? This was your circuit, and then there is this V in. V in could be anything. This was your 1 volt and this was your V naught. If your, let's just say if your V naught goes above 1 volt, what will happen? This will, let's just say this is 1.1 volt. If this is 1.1 volt, what will happen? This will become drain and this will become source. Right? What will be the current direction? This would be the current direction. If this is the current direction, then what will happen? The V naught potential will become negative potential, and which is not possible. This I explained you in the earlier part of video. Not possible. So V naught can never be drained. V naught can never be drained. If it tries to be drained, the V naught potential becomes negative, and if it is negative, then source is already at 1 volt. Source is already at 1 volt and drain you are saying negative. So this is not possible. If drain is negative, that means that has to be source and 1 volt has to be drain. So which is not possible. So maximum value V naught can attain is 1 volt. Say yes or no. At 1 volt, what will happen? Let's just when V naught is 1 volt, what will happen? VDS would become 0. If VDS becomes 0, then your ID would become, basically ID would not become 0. What I mean to say is that V naught will be 1 volt. That is the maximum value. So V naught value will be, what will be the maximum value? It will be around 0.99999 something. V naught can go up to 1 volt. It's not that it will go till 1 volt, right? because if ID becomes 0, V naught goes to 0 only. So basically it will rise from 0 and it will try to go towards 1 volt. That's it. So let's not write it. No meaning of writing it. So did you understand this point? The maximum value V naught can attain is 1 volt. And V in can be anything. When V naught is attaining 1 volt, what should be the value of V in? It has to be at least greater than 1.7 volt, right? It has to be at least greater than 1.7 volt. It can be 1.8 volt. Because let's just say if your V naught is 1 volt and your V in is 1.6 volt. Is that possible? Here your VGS would be 0.6 volt, which is less than VT. So that will turn off the transistor. If transistor is turned off, then V naught will go to 0 volt only. So it has to be at least greater than 1.7 volt. That's why 1.7 volt will come here only. Till 1.7 volt, V naught will never reach 1 volt. V naught is never going to reach 1 volt. Till 1.7 volt. It will be certainly lesser than 1 volt. After, it can reach towards 1 volt. Right there? After 1.7 volt. After 1.7. Well and good. So this is what I wanted to tell in this particular question. So that was actually a very good question. So I hope you have understood. In the examination, they can ask you this kind of waveform. In the interview as well, they can ask you this kind of waveform. So you should have the intuition to tell them like how I am treating this particular problem. So you will start with V in, okay, V in increases, then V in current will increase, then V naught will increase, but V naught will not increase as much as V in. Now if V in is increasing, it will keep on increasing, V naught will also keep on increasing, the region will also change from saturation to, the region will also change. Here what was the region of operation? Here the region of operation was saturation and here the region of operation was linear. The region of operation will also change, but the maximum value V naught can attain is 1 volt. It will be 1 volt. The maximum value V naught can attain is 1 volt. Lesser than 1 volt, somewhat lesser than 1 volt, it would be 0.9999999, because if it is 1 volt, the transistor will turn off, then V naught will be 0 volt. If transistor turns off, V naught will be 0 volt. So it will be some 0.99991 volt. So maximum value we can say it will be 1 volt. It cannot go above 1 volt. Why so? Because if it goes above 1 volt, V naught will be drain and 1 volt will be source, which is not possible. So all these things you need to tell in the interview, and in the examination, gate examination, they can ask you these kind of questions. They can ask you region of operation. They can ask you when will the transistor turn on. Here I made a mistake. What is the mistake that I did? It's good that I noticed it here only. So till 0.7 volt, V naught will be 0. Waveform is rising like this. I made a blunder here. So this waveform was wrong. Till V in equals to 0.7 volt. It will be in cutoff only, no? So this mistake I did here. This is cutoff and this is cutoff and this is saturation. This is cutoff and then it rises like this. Cutoff and rises like this, right? Till 0.7 it is in cutoff, from 0.7 to 1.7 it is in saturation, then 1.7 to next it will be in linear. So region of operation you can tell how will the waveform go, and maximum value also you can tell. So these kind of questions you will be very much comfortable answering. Well and good. Let's move towards our next question. Now these questions are also very important as well and also simple as well, simpler than all these things. In the first kind of question, what did we do? In the first kind of question, what did we do? We fixed the potential. There are no resistor, no capacitor. Vx value is getting changed. Here 1.9, here 1 volt. The potential is fixed. Then next kind of question, here we connected RL. The resistance we connected. Now we are connecting capacitor. So what will happen? Let's check that out. So here in this question, you have to draw two waveforms, Vx versus time t and Ix versus time t. And initial capacitor voltage is given, that is 3 volt. Initial capacitor voltage is given 3 volt. So if Vx is at 3 volt and this is at 0 volt, so certainly this will be drain and this will be source, right? This will be source and the current will flow like this only, right? Satisfied with that? Okay. So what we are going to do? We are going to write VGS, VT, all those values. So VGS is fixed here, that is 3 volt. VT is 1 volt. So what will be your V overdrive? That will be 2 volt. What will be your VDS? VDS will be VX, or you can say VC. VDS will be VX, or you can say VC. VX, VC, right? So at t equals to 0 plus, initially the capacitor is not going to change its voltage, it will be 3 volt only. So what is the VDS value? That is 3 volt. So at t equals to 0 plus, VDS is greater than V overdrive, right? VDS is greater than V overdrive. Transistor is in saturation region. If transistor is in saturation region, what will be the current? Current Ix. What will be the current Ix? That would be some constant into V overdrive square. V overdrive square would be this. So this will be the current. Now this current is flowing in this manner. In this manner, this current is flowing. What this current will do? It will discharge the cap. So at t equals to 0, what is the circuit? At t equals to 0 plus, MOS is acting as a current source only. MOS is acting as a current source. That has the value of K into 2 square. And then here there is a capacitor connected. So this capacitor is charged to 3 volt. And this is your Vx. The capacitor will start discharging. Capacitor will start discharging. And how it will discharge? Linearly. Why linearly? Because the current is constant. If the current is constant, what will be your Vx or VCT? That would be, initial voltage is 3, then the current is flowing in the opposite direction. The current is flowing like this. So 3 volt minus 1 by C integration I dot dt. 3 volt minus whatever the capacitor voltage is there and whatever the current is there, current I am calling it current I into T. So the voltage is going down from 3 to some voltage. From 3 to some voltage it will go down. So voltage will go down. You are drawing Vx versus time t. Vx versus time t. So initially your voltage was 3 volt. Now it is going down. Till what voltage it will go down? Till what time we don't know about that. But till what voltage it will go down? Tell me. When your VDS is equals to 2 volt. When your VDS is equals to 2 volt, what will happen? VDS would become equals to V overdrive. What I am writing? When VDS or Vx is less than 2 volt, that means your VDS would be less than V overdrive. VDS would be less than V overdrive because V overdrive is fixed, that is 2 volt. V overdrive is 2 volt. What will happen? MOS will go into triode region, and then in the triode region, what does the MOS acts as? The MOS acts as resistance. So in triode region, MOS will act as resistance. MOS, in the previous lecture we have studied it, right? MOS acts as resistance. So till 2 volt it is going. You don't need to tell the timing, but you need to tell the potential. When Vx is going down from 3 to 2 volt, till that potential will go linearly and the current will be constant. The constant current would be somewhat this. Ix we are drawing. Ix versus time t. The current would be constant and that constant current value is K into 2 square. K into 2 square till time t1. Till time t1. K into 2 square. So for time t greater than t1, most goes into linear region, and in linear region it acts as a resistance. So most will act as a resistance now. This is 2 volt now, right? This is your Vx which is at 2 volt now, and this is your Ix. What will happen? It will get discharged. Till what voltage it will discharge? 0 volt. Because when there is 0 volt here, Vds will become 0. If Vds is becoming 0, the current will be 0, right? Basically your Ix would be, what is your Ix? That is some constant into Vds. Vds is Vgs minus Vt. Vgs minus Vt is 2 into Vds, that is Vx minus Vx square by 2. We actually replace it with the resistance. We actually replace the MOS with the resistance in linear region. In linear region, MOS is replaced with the resistance between drain and source. R1 or R, whatever it is, R. MOS is replaced with the resistance, but there is an approximation. Do you remember that approximation? We approximate that VDS value is very small. So when we were deriving it, what was the expression? Some constant into VGS minus VT into VDS minus VDS square by 2. What I was doing? Del ID upon del VDS. So if I do del ID upon del VDS, what I was doing? I was considering this as 0 and VDS would be gone. So VDS would become 0. And this would be our fixed resistance. 1 upon this value would be our fixed resistance. So I made an assumption that my VDS value is very small. That was the assumption which we will not forget. So here what does it look like? That my Vx voltage will go down from 2 to 0 volt exponentially. But it will not be perfectly exponential. Why so? Because initially the VDS value is 2 volt, which is not very low. So it will go down, it will certainly go down, but not perfectly exponential. So now you can draw the graph of both Ix and Vx. So here I am writing both Vx and Ix will go down to 0. Will go down to 0, right? Both Ix and Vx will go down to 0. Now we can draw these curves. This was your Vx and this was your Ix. So I will draw it somewhat like this. I am not drawing it like this, then and then exponential. No. Why so? Because I made an assumption when I was deriving the formula of R1. I made an assumption that VDS is very small, but that is not exactly small. So I will not say that it will go down exponentially. In the interviewer, if the interviewer asks you, how will the waveform go? So you will not say, sir, it will certainly go down exponentially. No, no, no. Sir, nearly exponentially. It will be nearly exponentially, sir. Why it is nearly exponentially? Because when I am deriving the formula of R1, it has the VDS term. So this R value is not constant. It is depending on VDS value. But for our better expression, we take R value to be constant. But actually, it is varying, and it depends on VDS value, right? I told you when we were studying R1 R1 value, when we were studying about R1 value, I told you there as well that R1 is not constant. It depends on VDS, but since we are assuming VDS to be very small, you can assume it to be constant. But here VDS is not that small, so we have to take care that it will go down like this, but there will be something. There will be this. It will not be completely exponential. So this we have to take care. And here also I will make it somewhat like this, not completely exponential but somewhat exponential, follows the exponential nature but not completely exponential. So till this point it was in saturation region, and then it was in linear region. Here it was in saturation region, and then it was in linear region. So did you understand this problem completely? We started with, okay, 3 volt, 3 volt here. The transistor is in saturation region. If it is in saturation region, it will be replaced with a constant current source. It will go down, current will remain constant. But till what voltage it will go down in saturation region? Till 2 volt only. When Vc is equals to 2 volt, when it is equals to 2 volt, my transistor is going into linear region. So in the linear region, my transistor will act as a resistance. So now my voltage will go down exponentially, not linearly. So voltage is going down exponentially, but it is not perfectly exponential because R on value, the resistance R value is depending on the VDS voltage. So I cannot predict the waveform, but it is not completely exponential, that I can say. It is not completely exponential. And this is the Ix voltage. Well and good. Everything is crystal clear. Okay, let's move on to our next problem. This is the next problem. It is more intuitive. Try solving it on your own, then see the solution. So let's solve this question. I added one more thing. You have to find the minimum value of Vx. You have to tell the minimum value of Vx as well. Initial voltage is 3 volt. Initial voltage is 3 volt. One thing, what did you notice here? Here the drain and gate are shorted. Which will be drain, which will be source? This is at 3 volt. This is at 0. So this will be drain, this will be source. That's it. No problem. Here drain and gate are shorted. Drain and gate are shorted. What does it show? What does it show? It will be in MOS will always be in saturation. Saturation. So you can directly replace it with the current source, and Vc value will go from 3 to 0 volt like this. Wrong. Why so? Let's check that out, because it is not that straightforward, because this assignment is fusion special. So this is not that straightforward. What is your VGS? That is equals to Vx. What is your VDS? VDS is also equals to Vx. What is your V overdrive? V overdrive is VGS minus VT. That means Vx minus 0.7. Right? VT is 1. Okay. VT I am taking 1. VT is 1. V overdrive this is. It is in saturation region, that's for sure. What will be your Ix value? Some constant into V overdrive. This is your Ix value. I told you one thing. In saturation region, the current is constant. But when VGS is fixed, here VGS is not fixed. VGS is varying. VGS is depending on the value of Vx. So what is happening? It will act as a current source. Certainly it will act as a current source, but the current source is varying. The current source will change the value of Vx, and that change in the Vx will change the value of current source. Are you getting this point or not? The current source will change the value of Vx, and Vx will depend on the current source value. So basically you can replace it with the current source, but the current source is varying. So here how I will replace my circuit? This is a current source I, which will be a varying one. This is a current source I, this will be a varying one. This is your Vc potential, or Vx potential I should write. Vx potential. Initially it was charged to some voltage, then it will go down. And this is your Ix, which is a function of Vx. And this potential Vx is a function of Ix. Why it is a function of Ix? Because what will be your Vx? Vx will be initial voltage 3 volt minus 1 by C integration Ix t dot dt. Ix t dot dt. So what is happening in this circuit is that initially there is some current which is discharging the capacitor. If the capacitor is getting discharged, that means the current is also getting low. Then this low current is also discharging. What I mean to say is that this is a capacitor which is at 3 volt. Let's just say initially it was getting discharged with 2 ampere current. After some time it will be getting discharged only but 1.5 ampere current. After some time it will be getting discharged only but 1 ampere current. It is not getting charged. It is getting discharged only, but the amount of current is getting decreased. amount of current is getting decreased. Are you getting this point? So it is getting discharged, but the amount of current is getting decreased. So slowly the current is getting decreased, and also the voltage is also getting decreased. So how will your waveform look like? We will draw Vx versus time t and Ix versus time t. So initially your Vx was 3 volt, then it is going down. Now the question is till what voltage it will go down? Till 0 volt or some particular voltage? Tell me the answer of this. Till 1 volt only. Why so? Because when, okay, one thing I can tell here is that, so I will draw this waveform a bit downward. Here your Vx is going down. Here Vx is going down. And why did not I make it linear? Because Ix is not constant voltage. This is depending on Vx, so I can't make it linear. So that's why I had to make it something like this. This is not exponential. It is somewhat like some waveform that you don't know, but it will certainly not be linear. That's for sure. It will certainly not be linear. It will be somewhat waveform that you don't know. Here Vx is going down. Vx is going down. Till what voltage it will go down? Till what voltage? When your Vgs is less than Vt, what will happen? MOS will be turned off. MOS will be off. And if MOS is off, how will you replace the MOS? This was your cap, and your MOS will be open circuited, right? Because it is off, that means there is no current. So MOS will be open circuited, and this was the ground. This was your Vx potential. What is your VGS? VGS is Vx only. VGS is Vx only. When it is less than Vt, then your MOS will be turned off. So what is happening? The capacitor is getting discharged. It was getting discharged. At the time when this potential reaches 1 volt, after that let's just assume it tries to go to 0.99 volt. If it is trying to go to 0.99 volt, what is happening? This is saying that it is lesser than Vt. 0.99 is lesser than Vt, and if it is lesser than Vt, MOS will say I will not give any current. If it is not giving any current, then capacitor will not discharge further. So capacitor will remain at the 1 volt only. Are you getting this point or not? Understood? The capacitor was trying to discharge. It discharged till 1 volt. When it was 1 volt, the next potential was 0.99 volt. If you were getting 0.99 volt there, what the MOS will say? That it is lesser than Vt. If it is lesser than Vt, I will not give any current. If I am not giving any current, the capacitor has to hold its voltage. The capacitor has to hold its voltage. The capacitor is holding its voltage to 1 volt. So from 3 to its discharge till 1 volt. That's it. Understood this point? So this is actually a very important point which is oftenly asked in the gate examination. What is the minimum value of Vx? It will discharge till 1 volt only. Till 1 volt only. If Vx is less than 1 volt, there is no current. No current. And if there is no current, that means no further discharging. So till 1 volt only it will decay, and after that it will remain constant always. And constant. So let's just say till at some time t1 it reaches to 1 volt. After that it will remain constant. And what about your Vx? What about your Ix? Your Ix will go down. What will be the nature? You don't know. It will certainly be not linear or anything. Your Ix will go down and it will remain 0. At what time it will be 0? At t equals to t1 only it will be 0. Why at t equals to t1 only? Because at t equals to t1 you are reaching 1 volt. After that there will be no Morse current. If there is no Morse current, then this will be your Ix only. This was your Ix. There will be no Morse current. After that, there is no current. That means your Ix is equals to 0. So if Vx has reached to 1 volt, your Ix will be 0 only. So that's it. That would be the graph. In the examination, most of the time they will just ask you one simple question: what will be the minimum value of Vx? Then they will frame 4 options: 1, 0, -1, 2 volt. So answer would be 1 volt. Why so? Because till 1 volt it will discharge. That's it. Understood? So this is the waveform. So this was also a very conceptual question and very important with respect to gate examination. In the interview they can ask you anything, but in the gate examination this is very important for gate examination. Right? Let's move on to our next question. This is also very conceptual. Here I have connected 2 capacitors now. So both drain and source are varying. Both drain and source are varying this time. So what is the potential at drain? And we cannot call it drain. First we need to see the potential. What is Vc2 0 minus? That is 1 volt. And what is Vc1 0 minus? That is 3 volt. Which one will be drain? Which one will be source? You already know. Vt value is 0.7 this time. This time I have taken Vt value to be 0.7. You have to draw Vx1 versus T, Vx2 versus T, and Ix versus T. Very conceptual question it is. Those guys who have good idea of transient analysis, they can only solve this question. You have to get a very good idea of transient analysis, and I am pretty sure most of you guys don't have good idea of transient analysis. But that's why I told you, if you are studying analog electronics, please do have good idea of transient analysis. People will say that you can study analog electronics without studying transient analysis because they want views. But for actual understanding, for real understanding, for solving the question in the examination, for being confident, you should know the transient analysis first. Because I am going to highly use it in op-amp. When I teach op-amp, complete transient analysis will be used. How RC circuit is charging, what is switch capacitor. A lot of teachers in the gate industry don't even teach switch capacitor. Forget about all those things. They don't even teach switch capacitor. Every time they will include resistance. If there is no resistance, how the capacitor will charge, how capacitor will discharge, they will not teach it. Although whatever the concept is used, that I will teach here only. No need to worry about that. But do study network analysis as soon as possible. Okay, so try solving it on your own, then see the solution. So let's start the solution now. So here what do you see? Here your at t equals to 0. At t equals to 0 plus, I can write your Vx2 is 3 volt. Your Vx1 is 1 volt. One which is at higher potential, this is at higher potential, and this is lower potential. That means this will become drain and this will become source. So you have to interchange your circuit. So let's interchange it. Because this is becoming source now, so I have shown Vc2 here. This is the capacitor 2C, which is charged to 1 volt. This is charged to 1 volt, and this is the capacitor C. This is the capacitor C, which is charged to 3 volt. And this is 2 volt here. This potential is there Vx2 and the lower one is Vx1. This potential is Vx1 and this potential is Vx2. So Vx2 initially was 3 volt and this is 1 volt. Did you understand this diagram now? Did you understand this diagram? Say yes or no. The current will be flowing from this 3 volt. This is the potential which is at 3 volt and this is at 1 volt. The current will be flowing from 3 to 1 volt. So what is happening? The capacitor C is getting discharged and 2C is getting charged because from the positive potential the current is getting out. From the positive potential the current is getting out. That means the current would be getting in into the negative potential. If the current is getting in into the negative potential and if the current is getting out of the positive potential, What does that mean? The capacitor is getting discharged. This is the scene, plus minus. If this would have been the scene, this is 5 ampere current. Let's just say 5 ampere current. So the current is getting into the positive terminal. The capacitor is getting charged. If it was getting out of the positive terminal, that means capacitor is getting discharged. So here the current is getting out of the positive terminal. The current is getting out of the positive terminal. So C is getting discharged and 2C is getting charged. You can see the region of operation as well. What is your VGS? VGS is 1 volt. What is your VT? 0.7 volt. What is your VDS? 2 volt. VO drive is 0.3 volt. So until your Vx goes to 0.3, it will always be in linear region. Sorry, it will always be in saturation region. I'm really sorry. It will always be in saturation region, because here your VDS would be, here your VDS is greater than VO drive. That means it is in saturation region. So until this Vx2 minus Vx1, which is your VDS, is 0.3, then your VT will also change. So forget about the region of operation. For now it is in saturation region. We will check if there is something else or not. We will check. First let's find the steady state value. This is our task. Let's find the steady state value. First we got to know that it is in saturation region. There is a current flowing. That current will also not be constant. Why so? Because the current will also be the function of Vx1. Here the current would be flowing. Yeah, tell me what this current would be. Let's just call this current as Iy. So this current Iy would be negative of Ix, because Ix current is flowing from Vx1 to Vx2, but Iy current is flowing from Vx2 to Vx1. So this would be negative of Ix. So this Iy would be a function of Vx1 and also Vx2. Why also Vx2? Because Vx1 will depend on Vx2. So I should directly write it will be a function of Vx1. It will be a function of Vx1. Now there is a current source which is charging the capacitor 2C and discharging the capacitor C. What will happen in the circuit now? Till what voltage it can charge? What is the maximum voltage this capacitor 2C can get? Maximum voltage that 2C can get. What is the maximum voltage? This 2C is getting charged. Let's just say it is charged to 1.1 volt. What is VGS value? 0.9. If it is charged to 1.2 volt, what is VGS value? 0.8. If it is charged to 1.3 volt, what is VGS value? 0.7. If it is charged to 1.31 volt, what is VGS value? 0.69 volt. Is that possible? 0.69 volt. Is that possible? No. What will happen? The transistor will turn off. If the transistor is turned off, it will not supply any charge. So did you understand it? If your 2C is charged to 1.31 volt, the transistor will not supply any current. Transistor will turn off. So maximum value Vx1 can get is 1.3 volt only. So capacitor C can charge up to 1.3 volt only. The cap C shows that capacitor 2C can charge up to 1.3 volt only. Why so? Because if 2C charges above 1.3 volt, MOS will be off. MOS will be off. So Vx1 steady state, what will be your Vx1 steady state? That would be 1.3 volt only. Say yes or no. Vx1 would be 1.3 volt only. So when Vx1 was increasing, because Vx1 was increasing, right, from 1 volt to 3 volt, from 1 volt to 1.3 volt. there was IY current. There was IY current flowing out of capacitor C, right? So your capacitor 2C is getting charged from 1 to 1.3 volt. So this IY current was getting out of this, right? Say yes or no. Now tell me one thing, C and 2C, both of the capacitors are having the same current or not? Say yes or no. C and 2C, both of them are having the same current or not? Yes, they are having the same current. Both cap C and 2C are having same current. Same current. If both of the capacitors are having same current, like when the current in C is equals to current in 2C. What is the formula of current? That is the change in charge with respect to the time. The change in charge in C with respect to the time. Time would be certainly same. So the change in charge in C would be equals to the change in charge in 2C. What is the change in charge in 2C? What is the formula of charge? Q equals to CV. Say, whatever the capacitor is. So this capacitance of this 2C is 2C only. And what is the change in charge? It rises from 1 to 1.3. Rises from 1 to 1.3. Final minus initial. This is the change. What about the change in charge? The change in the charge of capacitor C, that we don't know. So what will be the change? Capacitance into the change in charge, that we don't know. So what that change would be? That change would be 0.6 volt. So basically there would be a change of 0.6 volt. Final voltage you don't know. Final voltage you don't know. Minus initial voltage you know. Initial voltage you know. So what is the initial voltage? Forget about this. You just know the change. You just know the change. That is 0.6 volt. And one thing I know, initially it is charged to 3 volt. Now there will be a change of 0.6. So it will go down to 2.4 volt because C is getting discharged. Say yes or no. Initially it was charged to 3 volt, right? There is a change of 0.6 volt, that I know. There is a change of 0.6 volt because the change in 2C is 0.3 volt. So there will be a change of 0.6 volt in C. One thing also I know is that it is getting discharged. So if initially it is having 3 and it is getting discharged, so finally what it will have? 2.4. Right or wrong? Right. Yes. So the change in capacitor, change in the voltage of capacitor C will be 0.6. Change in capacitor C voltage would be 0.6 volt. So Vx2 will go from 3 to 2.4. So Vx2 will, so capacitor will discharge, capacitor C will discharge from, capacitor C will discharge from 3 to 2.4 volt. So Vx1, is it Vx2? Okay, Vx2. Vx2 will decay down from 3 to 2.4 volt. Say yes or no. Did you understand it or not? When you saw the circuit, you got to know that this is acting as drain, this is acting as drain, this is acting as source. So you made this circuit. Then you what did you get to know? You got to know that the current will be flowing like this. Right? The current will be flowing like this. That means it is charging the capacitor 2C and discharging the capacitor C. Till what voltage the capacitor 2C can charge? That is 1.3 voltage. Till 1.3 only it can charge. Because after that the current will be 0. So till 1.3 it will charge. If it is getting charged till 1.3, that means it is gaining 0.3. then how much C would get? 2C into 0.3 would be equals to C into the gain. 2C into 0.3, 2C into 0.3 into equals to C into the gain. So the gain would be 0.6 volt. It can be gain also, decay also, but you got to know that it is decaying. So from 3 to 2 point, from 3 to 2.4 it is going. So steady state voltage. So VC1 steady state, VC1 steady state would be what? 2.4 volt. Say yes or no. What an amazing question it was, right? So these kind of problems, these kind of concept are only found on PrepFusion. Marketing करना तो पड़ेगा यार, इतना मेहनत कर रहा हूँ तो मार्केटिंग तो करना बनता है. तो now we are going to draw the waveforms. What waveform did they ask? Vx1 versus t, Vx2 versus t, and Ix versus t. So for Vx1, it started from 1 and rises up to 1.3. Started from 1, rises up to 1.3, and that will be the steady state. Let's assume it reaches the steady state at time t1. This is the time t1 when it reaches the steady state, and voltage is 1.3 volt. What about Vx2? It starts from 3 volt and goes till 2.4. What is this? This is not exponential. It can be anything because Vx1, Vx2, Ix all are function of each other. All are function of each other. So it can be anything. It rises to, it goes down to 2.4 volt and then remain there as it is. This will be 2.4 volt. By the way, you can at steady state, I will draw the circuit now. At steady state, what is the scene? Here only I can draw. This is 2.4. This is 1.3. And this was 2, right? So here what is your VDS? VDS is 1.1 volt. And what is your VDS is 1.1 volt. What is your VGS? That is 0.7 volt. And VO drive will be 0 volt only. So again it is in saturation region only. So we started from saturation. Here I told you we started from saturation, and we always remained at saturation only. So the region of operation is not that important, but we always was in saturation. We can check it the initial condition at the final condition. So we were always in saturation region. After that, certainly we will go into cutoff. So this is the cutoff. This is saturation. This will be cutoff. And what about Ix? Ix will slowly decrease. Why it will slowly decrease? Why it will slowly decrease? Because VGS potential is getting decreased. VGS is getting decreased. Also VDS is also getting decreased. But you don't need to think about VDS because we are running in saturation region. So if you are running in saturation region, you only need to think about VGS. So VGS is getting decreased, so current will also decrease. And when Vx reaches 1.3 volt, when Vx reaches 1.3 volt at time t equals to t1, when Vx reaches 1.3 volt, the current would become 0. Current would become 0 when Vx reaches 1.3 volt. After that, the current would be 0. Say yes or no. Well and good, understood? Crystal clear? So you can revise it once again. I hope I have explained it in a very good manner. You can revise it once again. Then we can move on to our next question. So I will frame one more question that will enhance your knowledge more. So I will frame one more question here. Then we can proceed to our next question. So let's start this question now. So this question I have framed just now only. What it is saying, Vx2 value for t less than 0 is 2 volt. So this capacitor is charged to 2 volt. and this capacitor is charged to 1 volt. So here I don't need to interchange. So I reduced the problem. I don't need to interchange here because this is drain, this is source. So drain is already at higher potential. I don't need to interchange it. Vt is 1 volt. Vt is 1 volt, that is given. You have to find the steady state value of Vx1 and Vx2. Steady state value of Vx1 and Vx2. So what should be the steady state value of Vx1? Vx1 steady state. What will happen? This is drain, this is source, there will be current here. There will be a current flowing here that will charge the capacitor 2C. So 2C can charge up to what voltage? It can go to 1, 1.1, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt. When it reaches 7 volt, what is your VGS value? 1 volt. If it is going to 7.1 volt, what will be your VGS value? VGS value will be 0.9 volt. At that time, your MOS will turn off. And if MOS is turning off, then there will be no further current and capacitor will hold its voltage. So it will charge up to 7 volt. So Vx1 steady state will be 7 volt. This is not the final answer. Those who have got the final answer, they have to wait. Just wait. I will solve it. I will give you the final answer. So Vx1 steady state is 7 volt. So if it is 7 volt, then how much voltage it has increased? 6 volt, right? From 1 to 7 it went. Vx1 went, the capacitor 2C went from 1 to 7 volt. 1 to 7 volt. So if I apply that charge conservation that I applied there, because the current is same, so 2C got 6 volt. So how much C will get? How much voltage C will get? 2C, the charge is the charge that 2C got, that was 2C into 6 volt. Here in the previous problem we solved it, no? What is the charge that capacitor C stored? C into delta Vc. And what is the charge 2C stored? 2C into the change in voltage. Change in voltage was 1 to 1.3. So 1.3 minus 1. So similarly here 1 to 7. So change in 6 volt. And 2C will have delta Vc. So delta Vc would be 12 volt. And if delta Vc is 12 volt, this 2 volt is, this capacitor C is getting discharged. This capacitor C is getting discharged. C is discharging. C is discharging. If C is discharging, then initially it was having 2 volt, then it will discharge by 12 volt. It will discharge by 12 volt. So what will be your Vx2 steady state? It was 2 volt and then it will lose 12 volt. So Vx2 steady state would be minus 10 volt. And this whole analysis is wrong. Right? Why so? Because here you told that it will rise up to 7 volt. Okay, fine. Because VGS would be greater than VT. Now you are saying that it will decay till minus 10. That means this will be the scene. This will be the scene. It will decay till minus 10. You can write in this manner that it will decay till minus 10, then I can improve it like this. Is that possible? Your drain is at minus 10, your source is at 7. Is that possible? No, this is not possible, right? We are in the previous question we considered this equation that your VGS should be greater than VT. But did you consider this equation as well, that your VDS should be greater than 0 as well? For the transistor to turn on, your VGS should be greater than VT, but your VDS also should be greater than 0. Are you getting this point or not? Your drain to source voltage should also be greater than 0. This is the condition as well. So you have to consider that as well. Now we will solve the problem correctly. In the previous problem, I did not care about it. Why I did not care about it? Because at the steady state, I could see that my VDS is 1.1 volt. So here I could see that my VDS is already greater than 0 volt. So this is also one of the conditions that you need to take care. But here I could see that what is my VDS? Here my VDS is, this is minus 10 and minus 10. This is minus 10. Drain is minus 10. And source is at, source was at 7 volt. Vx1 was 7 volt. Vx1 was 7 volt. Source was at 7 volt. Minus 17, which is wrong. It cannot be like that. So now I have to take care of the condition that your VGS, so your VDS should be greater than 0. So this is our circuit. This is 8 volt. 2C. This is 1 volt. C. This is 2 volt. Now there is this current I. This is your Vx, Vx2, and this is your Vx1. Let's just assume if there is a current I flowing, both of them are having the same current. The current in 2C would be the same in current in C, right? Tell me one thing. If this 1 volt is developing, if this 2C is developing X voltage, then how much voltage this 2C will lose? Are you getting this point? That C is getting discharge. C is discharging and 2C is charging. So if 2C is getting X amount of voltage, if 2C is getting X amount of voltage, then how much voltage C will lose? If 2C is getting X amount of voltage, then how much voltage C will lose? Let's check that out. Let's check it out. So let's assume that if both of the current are same, that means the charge, that is change in charge, would also be same. The change in charge would also be same. So what is the change in charge in case of 2C? That would be 2C into change in charge. Change in charge. Let's just call it delta V into 2C. The change in charge. That is delta V into 2C. What will be the change in charge in this one? That would be delta V into C. So what is the relation? Delta V into C would be equals to 2 into delta V to C, right? This is the relation. The change in voltage, the change in voltage of C would be twice of the change in voltage of 2C. Let change in voltage of 2C is X. That means 2C is gaining X voltage. 2C is gaining X voltage. So what will be your Vx1? Vx1 steady state would be 1 plus X. So if it is gaining X voltage, then how much C will be losing? 2X. Because capacitance value is half. If capacitance value is half, it will lose 2X. If it is gaining X, it will lose 2X. Say yes or no. In the previous program, what was happening? Here it was gaining 0.3, 1 to 1.3. So it was gaining 0.3. So it was losing 0.6. It has gained 0.3. So C was losing 0.6. Say yes or no. So similarly, here, if it is gaining X, then how much 2C will lose? How much this C will lose? C will be losing 2X. If 2C gains X voltage, then C loses 2X voltage. Say yes or no. What will be your Vx2 steady state? That would be 2 volt minus 2X. 2 volt minus 2X. It was gaining X voltage and it was losing 2X voltage. It was gaining X, it was losing 2X. So if it was gaining X, 2Cx would be the charge. And if I was losing 2X, then what will be the charge? C into 2X. So 2Cx, right? So this is the Vx2 steady state. Vx2 steady state. And one thing I know that at steady state, what will happen? Your VDS will be 0, because if VDS is 0, the current I would be 0 ampere. So that is the steady state voltage. So VDS is 0. That means Vx1, what is VDS? VDS is Vx2 minus Vx1. Vx2 minus Vx1 is equals to 0. So Vx2 is equals to Vx1. So 2 minus 2x is equals to 1 plus x. X will be 1 by 3 volt. X will be 1 by 3 volt. X will be 1 by 3 volt. So what will be your Vx1 steady state? That would be 1 plus 1 by 3. 1 plus 1 by 3 would be 1.33 volt. And what will be Vx2 steady state? 2 minus 2 by 3. 2 minus 2 by 3 would be what? 1.33 volt only. Of course, both has to be same only. 2 minus 2 by 3 would be 1.3 only. Say yes or no. Did you understand it or not? We tried to solve it. We tried to solve this problem in the same manner that we studied. So what we have studied, that the 2C can charge up to 7 volt. So we did that. When we did that, what did we get to know? That if 2C is getting charged to 7 volt, if 2C is getting 6 volt, then C will lose 12 volt. If 2C is getting 6 volt, then C will lose 12 volt. If C is losing 12 volt, then what is happening? The C will be at minus 10. C will be at minus 10. Source will be at 7. That means so VDS is going very low. You take care of the condition of VGS greater than VT, but you forgot about the condition of VDS greater than 0. In the previous question, we took care of VGS greater than VT. We took care of VGS greater than VT, then we checked if VDS is greater than 0 or not. Yeah, it is good. Well and good. Here, we took care of VGS greater than VT, but we forgot to check of VDS greater than 0. Then we got to know that VDS is not greater than 0. Then what did we understand? That we need to take VDS equals to 0. If VDS is equals to 0, that will be the steady state. Because if VDS is 0, there will be no current. So capacitor will neither charge nor discharge. So they will hold their voltage. If VDS is 0, there is 0 current. If there is 0 current in the MOS, then capacitor will hold their voltage. Right? Then what we know? If 2C is getting X voltage, if 2C is getting X voltage, then C will lose 2X voltage. If 2C is gaining X voltage, then C will lose 2X voltage. That's it. So C was having initially 2 volt, then minus 2x, and it was having initially 1 volt, then plus x. So 1 plus x, and this will have 2 minus 2x. And at steady state, VDS will be equal to 0. So both of the potential will be equal to 0. If both of the potential are 0, then I could get the value of x. That was 1 by 3. So Vx1 steady state would be 1.33 and Vx2 steady state will also be 1.33. So that was an amazing question. 2 questions I have shown you. I hope you are very much comfortable with all those kind of concept. Well and good. We can solve more question like that. So we will solve more question because that is an important part for your preparation. But let's see it later on. We first solve the question that is already given. Okay, so here VC1 is 3 volt. This is given. And VC2 is 1 volt. It is also given. Right? So what will be your Vx1 at t equals to 0? Vx1 at t equals to 0 plus 3 plus 1, it will be 4 volt only. And what will be your Vx2 at t equals to 0 plus? That will be 3 volt only. So this will be your drain and this will be your source. So this is your drain and this is your source. And this is certainly gate. Know about that. What is your VGS value? 2 minus 3, which is equals to minus 1, which is less than VT. MOS never turns on. MOS doesn't even turn on. This is the steady state. Ix is equals to 0. There is no current in the MOS. Ix is equals to 0 and this is the steady state. That's it. What did we get to know? Here we get to know that your VGS is less than VT. That means MOS is never turning on. There is no current, nothing. The capacitor will hold their voltage. There is no current, no source. So capacitor will just hold their voltage. So you have to draw Vx1 versus T and Vx2 versus T. Right? Vx1 versus T and Vx2 versus T. थक गया भाई ये लेक्चर रिकॉर्ड करता करता मैं. लाइक तो बनता है. You should give a like. Right? If we are explaining these kind of concept, you should certainly put a like at least. Vx1 versus T, Vx2 versus T, and Ix versus T. Always 0 ampere current. And I strongly, highly recommend you to study network analysis from PrepFusion once. Please study network analysis from there. In network analysis, you will see a lot of these kind of concepts which are not taught to you in your gate preparation or even for placements. And in the examination, in the interview, you face these kind of question and everything goes blank. It affects your complete examination as well. So whatever the subject we study, we will build so much of strong concept in that. No matter how tough the question is framed in the examination, you will be able to answer, and that is my promise. So always 3 volt will be there, and Vx1 will always be at 4 volt. Vx1 will always be at 4 volt, and Vx2 will always be at 3 volt, and the current will always be 0. This was 4 volt, and Vx2 will also be like this. So it will always be at 4 volt, it will always be at 3 volt. That's it. And this will always be 0 ampere. Any doubt about that? No doubt, right? So this was the question. Let's move on to the next problem. This is the problem. So for t less than 0, Vin is 0. And for t greater than 0, Vin is 3 volt. So whenever there is a step input applied, this is step, right? This is step input. So whenever there is a step input applied from 0 to some 3 volt, then you always need to solve the problem from minus infinity. In the network analysis, I also told you, if we are having some step, you will always solve from minus infinity. You have to take the condition of t less than 0 as well. For t less than 0, what was the scene? For t less than 0, here we are solving the problem. So for t less than 0, Vin was 0. If Vin was 0, VGS was 0. Vin was 0 volt, VGS was 0 volt. No current. So V naught at t equals to 0 minus would be same as Vc at t equals to 0 minus. That would be equals to 1 volt. Here I did not mention that Vc voltage is 1 volt for t equals to 0 minus. I have to understand it by my own. In the previous problems, it was given that at t equals to 0 minus, this is the voltage. But here in the diagram, it is just shown that it is at 1 volt. That's it. You have to start the circuit from t equals to 0 minus or t equals to minus infinity. You have to start the circuit from t equals to minus infinity. You have to take the condition from minus infinity to 0. You have to take the condition from minus infinity to 0. Then you need to proceed from 0 to infinity. So in the complete window, you have to solve the problem. So for lesser than that, there was nothing happening in the circuit. So luckily in this problem, even if you have started from here, your answer would be correct. Because previously nothing was happening. But I will give you one more question where previously something was happening. So then your answer will not be correct. So luckily in this question, you are safe because previously nothing was happening. So VC voltage was at 1 volt only. Now for t greater than 0 or at t equals to 0 plus, Vin is 3 volt. Vin is 3 volt. And the capacitor is at 1 volt only. So we can draw the circuit now. Vin is 3 volt. This is grounded. Capacitor is at 1 volt. And this is your V naught. What will happen? The current will flow, right? Say yes or no. What is the VDS value here? VDS value is I can call it, is it V naught or Vx? V naught. So VDS value is equals to V naught. And at t equals to 0 plus, if you are talking about, that is equals to 1 volt. What is VGS value? That is 3 volt. And what is VT value? 2 volt. So V overdrive is, VT value is 1 volt. No, why I am writing 2 volt? VT value is 1 volt. So V overdrive is 2 volt. It is working in linear region. You can see it directly because VDS is lesser than V overdrive. So it is working in linear region. So it can be replaced with the resistance. If it is replaced with the resistance, what will happen? The capacitor will discharge. This is 1 volt. The capacitor will discharge, and till what voltage it will discharge? Till 0, because here VGS is always greater than VT. VGS is always greater than VT. So you don't need to think about this condition, but you have to think about this condition, that VDS goes to 0. If VDS goes to 0, then it will be discharged to 0 volt. Always you need to take care about two conditions. VGS is greater than VT. If your VGS is greater than VT, checked, nothing. Now your VDS will be going towards 0. So your VDS will be going towards 0. I needed to plot V naught versus V. What did I needed to plot here? V naught versus time t. So V naught initially was at 1 volt and it will decay down to 0 volt, right? And it will remain at 0 volt only. And this was working in linear region. In the previous question, which I took here I did not draw any waveform or anything because I just simply asked you the question, what will be the steady state voltage? Now people will say these kind of questions are not asked in gate examination, but certainly it will come. I can write it on paper and sign it. In the gate examination, always the question for condition VGS greater than VT has been asked. For the condition VGS greater than VT, it has been asked in the gate examination. Certainly there will be one question which will ask you for VDS greater than 0, and that will be the solution. So be prepared for that. It is certainly coming. In 1 or 2 years, it is certainly coming. The kind of paper, the kind of level they are setting up, certainly these kind of questions are coming. So don't fall for the teachers or even for any educator. They say that these kind of questions are not asked, this concept is not asked. The reality is they are afraid to take up these kind of questions on blackboard. They are afraid to take up. This is the reality. It may seem disrespecting to some people. It may sound harsh to some people, but I'm really sorry. This is the reality that I'm telling, that people are not really fond of taking tough examples, because what teachers think is that if I am dealing tough examples, the crowd will not come to me. And this is the reality. If I teach these kind of tough concept, the students will not be happy. They will not be coming. Okay, I will study from him, because the student has to put some stress on the brain. But if you are not putting the stress on the brain, you are not going to get good rank. Ask many of the previous year aspirants. They studied simple thing only. You will keep on studying simple thing. In the examination, they will ask you tough questions. If you are preparing for 365 days, for 364 days, you will be very happy. On the 365th day, you will write down the examination and you will be disappointed. Or even if you crack the examination, in the interview, you will be disappointed. I can guarantee. In the interview, in M.tech MS interview, you will be disappointed. Even if you crack the interview while going for placements, you will be disappointed at that time. So yeah, just study thoroughly whatever that I am teaching. I am not taking much of your time. I am taking certain time that is required. It's not that I am blindly teaching anything. I know a lot of things as well. I know more things. Motorola Wising, all those things I am not going to teach in the complete network, in this complete analog course. But whatever that is required, that is need to be taught, right? Yeah. So this was the question we have solved. Now let's move on to our last question. So this is the last question. So here Vt is 1 volt that is given. You have to draw Vx versus T curve. And again there is a step input. I told you if there is step input, you always have to start from t equals to minus infinity or t less than 0. So for t less than 0. So for t less than 0, what is the circuit? This is the circuit for t less than 0. Here again your VGS is 0. Again your current will be 0. Nothing will happen in this circuit as well. Right? For t less than 0, nothing will happen here. Current is equals to 0. This is the steady state only. So let's call this potential as Vx. Not Vx, sorry, it will be Vc. So your Vc for t equals to 0 minus would be 2 volt only, and that will be the same for Vc equals to Vc at t equals to 0 plus. Now let's see the circuit for t greater than 0. What is happening? This is 2 volt and here there is 3 volt and this is Vx. So your Vx potential here, what was your Vx potential? Vx potential for t equals to 0 minus. What was the Vx potential? This was 0 and this would be 2 volt. So what will be your Vx potential at t equals to 0 plus? This was 3 plus 2, 5 volt. Vx potential at t equals to 0 plus, this was 5 volt, right? And since now what is happening? Since this is 3 volt here and Vx potential is 5 volt. What is your VGS? VGS is 3 volt. What is your VDS? VDS is 5 volt. What is V overdrive? V overdrive is VGS minus VT, that would be 2 volt. So here VDS is greater than V overdrive, saturation region. So there will be a constant current here, that is this ID current, and that ID current would be some K into, in saturation region, some K into VGS minus VT 2 square. So there will be some ID constant current. Now where will this ID current would be flowing? The current would be flowing like this, right? Because this is the ID current, this Vx is an open end, so that current has to go here. Now people will say, sir, here there is 0 ampere current because gate drives a 0 ampere current. So from where this current is coming? From the battery. This ID current is flowing like this. This is the ID current. ID current will flow like this. This will be the path of the ID current. What will be the path? This is 3 volt battery. This is the battery of 3 volt. From 3 volt battery to the capacitor, and then there is the MOS circuit. This will be the path. MOS. This will be the path of ID. From 3 volt battery, ID is coming and going like this. Input current is 0, but battery can drive some current. No, this is a battery. 3 volt we have shown by the dot, but there is a battery of 3 volt. So battery can drive a current. No. People get confused often that, sir, there will be no current in the 2 volt voltage, 2 volt capacitor. So that's the steady state. That's it. No, bro. Battery can drive some current, right? Battery can drive it. Yeah. So what this current will do? It will charge the capacitor in the opposite direction. It is charging the capacitor in the opposite direction. What did we consider? This we consider Vx. So it is charging the capacitor in the opposite direction. Yeah. So this was not Vx. This was Vc. So it is getting charged like this. Now tell me, Vx value will go up or go down? Vx value will go up or go down? What is the initial Vx value? 5 volt. Now what will happen? This 2 volt will be reducing because it is getting charged in this direction. Let's just say this capacitor is having 2 volt and now the current is flowing out of it. What will happen? This will go to 1 volt. It will reduce. The similar thing is happening like this. The current is getting out of the positive terminal. The current is getting out of the positive terminal. So the capacitor is getting discharged. Right? The capacitor is getting discharged. So capacitor is getting charged in opposite direction. Charged in opposite direction. So it is getting charged in opposite direction. What does that mean? Vc value will decrease. Vc value will decrease. If Vc value decreases, then what is your Vx potential? Vx potential is 3 plus Vc. That means your Vx will 3 plus Vc. Why I am writing Vx? 3 plus Vc. That means your Vx goes down. Your Vx is going down. So you started from 2 actually. You started from 2, then there was a sudden jump to 5, then it is going down. Now it is going down. How it is going down? It is going down with the constant slope because Vc is constant. What is Vc? Vc is initial was 2, then 1 by c integration I dot dt. I is constant now. 2 minus 1 by c. What is I? I is constant. I is constant. That is 4k. So I is constant. So Vc will go down constantly. So even Vx will also go down constantly. So Vx versus T we are drawing. So initially it was at 2 volt. Then there was a sudden jump to 5. Then it is going down. So from 5 to till what voltage it can go down? From 5 to till what voltage it can go down? Here Vgs is always greater than Vt. V overdrive is always greater than 0. So that is certain that it will always be on. There is no issue with that. The other point is you need to check VDS value. So for VDS needs to be greater than 0. VDS needs to be greater than 0. For transistor to turn on, VDS should be greater than 0. VGS is always greater than VT here. This is your VGS. VT was 1 volt. VGS is fixed, that is 3, and VT was 1. So this is fixed. These voltages are fixed now. These voltages are fixed. VT was 1 volt. Transistor is on. There is no issue with that. Till what voltage Vx can go down? If Vx is going towards 0, if Vx goes to 0, after that it cannot go down. Why so? If it is go down, then that. If it goes down, then 0. Let's just say if it goes down to 0.1, what will happen? VDS value will be minus 0.1. Now, no one will say that, sir, if this is going down, that means this will act as source and this will act as drain. If that happens, then what will be the direction of current? The direction of current will be like this. Now the capacitor will charge. If the capacitor is charging, then again Vx will go up. Did you understand this point? I explained it very fastly. What did I say? The Vx cannot go down from 0. If I say that Vx is going down to minus 0.1, what will happen? This is at minus 0.1 and this is at 0. Then you will say that, sir, this will act as drain and this will act as source. Okay. If this is happening, then the current will be flowing from drain to source. Current will be flowing in this direction. The same current will be flowing in the capacitor in this direction. Then the capacitor will charge. So if the capacitor is charging, then Vx voltage will go up. Because what is the Vx voltage? 3 plus Vc. So if Vc is going down, then Vx voltage will go up. So you reduce this to minus 0.1, but it is going again towards 0. So again it will be higher than this 0 potential. Again it will go to 0.1. Then again you will say this is drain and this is source. Then again you will start following the current in this direction. Then again you will say that, sir, Vx is going down. Again you will say, sir, Vx can go up to minus 0.1 volt. Again the same thing will happening. So it will not go like that. What it will say that if I am going Vx equals to 0, at that time only I will stop. That's it. That will be the steady state. So steady state Vx voltage will be 0. In the previous questions as well, this doubt may come to you. Like in what questions? Let me show you. The same doubt might have occurred to a lot of students in the previous questions. Like I guess in this question also that same doubt would have come that, sir, it is going towards 0. What if it goes towards minus 0.1? Let's say it goes towards minus 0.1 and this is 0. Then what will happen? The current will flow in this direction. If the current flows in this direction, this will charge the capacitor. This charges the capacitor, that means it will rise to, from minus 0.12 it will rise to 0, then again 0.1. If again it is happening, again it will become drain and again it will become source. Again it will discharge. So basically the steady state voltage is 0 volt only. So it cannot go down 0 volt. Are you getting this point? If it goes down to 0 volt, there is a lot of things happening in the circuit. If it is goes down 0 point minus 0.1, that means it will say the current should flow in this direction. That will again charge the capacitor. Again it is charging the capacitor, again it is going up. So basically the steady state voltage is 0 volt. So the kind of feedback is working there. What is feedback? You don't know, but you will study it in the analog electronics. In the whole course, you will study it. Kind of feedback is working there. It is saying that if it is trying to going down from 0, if it is trying to going down to minus 0.1, then it will rise up again to 0 volt. It will get a force to rise up again to 0 volt. Yeah, so it will linearly rise, but till what point it will linearly decay? It is linearly decaying, but till what point it will linearly decay? Because what is VDS? VDS is equals to Vx. And what is V overdrive? V overdrive is 2 volt. When Vx is less than 2 volt, you will get into linear region. And in the linear region, this will act as a resistance. And this will be the gap. So when Vx is equals to 2 volt, this will be the same. So when Vx equals to 2 volt, you started from here only. When Vx equals to 2 volt, till this point it is working in saturation region. After that, it will nearly decay exponentially. Nearly exponentially. Why nearly? Because R depend on the value of Vx as well. So nearly exponentially. So this region would be linear. And this voltage we will be getting at some time t1. So steady state voltage of Vx is 0 volt. There is no doubt about that. But it will decay like that. If they ask you what is the steady state voltage of Vc, tell me, what is that? Vc steady state. Vc steady state. Okay, this is the question I am leaving for you. You have to write down the final answer in the comment section. You have to write down the final answer in the comment section. I will write down the final answer in the comment section as well. I will also write down the final answer, but you have to write down the final answer. What is the Vc value at steady state? This is very simple. What is the Vc value at steady state? Very simple it is. Okay, you will write it down. Vc direction is this. Take care of the direction. So what is the Vc value at steady state? This you need to write down in the comment section. So I hope you have understood this problem. In this problem, we saw initially there is 2 volt. Okay, then 5 volt is coming. There will be a current. The current will be from the saturation region. So that current will be charging the capacitor in the opposite direction. That means Vx will be going down. If Vx is going down, it will go down till 2 volt in linear region. After that, it will go down. Sorry, till 2 volt it will go down in the saturation region. After 2 volt, it will go down by the linear region. So it is going like that. So till 0 volt it will discharge, and if Vx is 0 volt, what will be the Vc value at steady state? That is very simple. You can tell that. What will be the Vc value at steady state? That I am expecting in the comment section. And if you liked the video, if you found the video helpful, please do share it with your friends. Please do share it. Please tell them what kind of content is being taught on this channel, what kind of content is being taught in the whole analog electronics. In the whole analog electronics, you will see a very different kind of analysis, a very intuitive, and you will put pressure on your brain, and in the examination you will be very happy once you come out of the examination hall, that we studied in that manner and that depth, and no one can beat us. That's for sure. So yeah, do share it with your friends and everyone. So let's meet in the next lecture. We will study further things. Okay, thank you.